Suzuki reaction. The Suzuki reaction is basically a reaction between vinylic halide or arylic halide with organoboron compounds such as boronic ester in the presence of base and palladium catalyst to give a compound that has a new carbon-carbon single bond. Here are some examples for the Suzuki coupling reaction. In each of these reactions, the R group of the vinyl halide or aryl halide is coordinated with the R group of the organoboron compound to form a new compound with a new carbon-carbon single bond. Here are the new carbon-carbon single bonds that are formed. In the case of vinyl halides, the configuration of the double bond is retained in the product. Okay, say for example, here the two groups are in trans position with respect to each other, and even in the compound, even in the product, the newly added alkyl group is in trans position with respect to this methyl group. So trans gives trans, and therefore this reaction is stereospecific. In the next example, you could see that this is a trans Alkenyl-Boron, Organoboron, right? Where you can see that the hydrogens are here and the two bulky groups are on opposite sides, right? And in the product also, the double bond is trans. The mechanism for the Suzuki reaction is still not understood completely. However, the mechanism that we are going to go over right now has got some experimental evidence. So let's take a look into that mechanism. First, to begin with, the palladium catalyst is going to get inserted between the carbon and Br of the aryl or vinyl halides. This step, where the metal is getting inserted between two atoms, is called as oxidative addition. In the next step, since we are using hydroxide ion as a base, the hydroxide ion will go and substitute for the Br. Okay, so this will go and attack here, thrust this Br out. And it's going to form this complex. Now this complex is going to react with our organoboron compound, where these electrons that is present on oxygen will be donated onto this boron. And in the next step, the R group will be transferred onto palladium, and this bond will be pushed onto oxygen, which has a positive charge, and this whole thing is going to leave. This whole thing will be leaving. Now the last thing that needs to happen is we needed to kick out this palladium, so a new carbon-carbon bond can be formed between the two R groups. This step, where the metal is eliminated from the two atoms, is called as reductive elimination. And this will also generate as the catalyst, which can be used to react with another molecule of the aryl or vinyl halides. Now, how to prepare the organoboron compound that is required for the Suzuki coupling reaction? It is generally prepared by the hydroboration reaction of a terminal alkene or terminal alkyne. Here are two examples, one with terminal alkene and the other one with terminal alkyne, and in both of these cases we used catechol-boron. We know that hydroboration is a syn addition reaction, okay, where the two groups that are getting added will be added to the same side of the molecule. So here between these two carbons, which of these is going to get the boron? Which one is the electrophile here? Obviously boron is the electrophile. So the electrophile will always get added to the carbon which has the most number of hydrogens, right? So between these two carbons, this is the carbon which has got more number of hydrogens, and therefore the boron substituent is going to go on here, and the hydride ion is going to go to this carbon. So you can see that the hydrogen has been added onto this carbon, right? This is a new hydrogen that has been added, and the boron is getting added to the other carbon. Applying the same thing here again to terminal alkyne. So between these two carbons, which one is going to get the boron? Obviously, this is the carbon which has the most number of hydrogens, and therefore this is the carbon which is going to get the boron, and the other carbon is going to get the hydride ion. While the boron and the hydrogen are in the same direction, the boron and the R group are in opposite directions. So the double bond that you get in the Alkenyl-Boron will always be trans. So you can see that these two groups are opposite to each other, right? So this double bond is always trans. This is the Alkenyl-Organoboron. If you want to synthesize the Aryl-Organoboron compound, then you have to start with aryl lithium. aryl lithium, when reacted with trialkyl borate, it will give us the Aryl-Organoboron compound. So this is basically a transmetallation reaction. We know that the organolithium compounds are very reactive because you can see that this bond right here is more polar. This carbon will be acting as a nucleophile on this electrophilic boron, and in place of lithium you now have this group. So while this is a more polar bond, by converting into another organometallic compound, you should have a less polar bond.